So should I be able to
you
share my
should actually
screen?
just be able to share screen directly, or I can enable that if you.
Yeah, it's disabled for now.
Or if you prefer, I can share the slideshow and then I can just advance for you, whichever is easier.
All right, it would be better for me to share my screen, so
Okay.
I could control. But it's still disabled, so. Okay.
Could you try sharing now?
Yeah, now it's working. Just tell me if yeah, just a second. Okay, can you see my presentation? Yes, it's good. Fine. Okay, so let's start. Yeah, so hi everyone. I'm really happy to be here, even remotely.
So one
yes.
second, we are not getting you over the audio system for some reason.
Okay. Should I keep talking? So it's a problem on your end, I understand.
Could you just keep talking so we can quickly test this?
Yeah. Okay, I can tell you that I might take a few breaks to drink water from time to time because I've caught a cold. So yeah, sorry about that. Maybe it's a good thing it's remotely. And yeah. Test 1, 2.
Ev, can you say something?
Yes. Test. Does it work? Is it better?
Yes, you're fine. Go ahead.
Okay, great. All right, so let's dive in. So I'll start with an overview of what is going on with the Hubble constant. I'll explain how it can be measured with time delay cosmography. I'll discuss the current analysis method and its challenges. I'll present how a neural ratio estimator can help us to address these challenges. I'll describe the framework we are working with. I'll show the current results, and I'll mention a few next steps. So first, the Hubble constant. As you know, it is today's expansion rate of the universe. It is important because it is one of the main parameters of the lambda CDM cosmological model. So it has an impact on many fields in astrophysics. There are two main categories of methods to measure H0. The first one rely on early universe probes, like the cosmic microwave background. And these methods are indirect and model dependent. The second category uses late universe probes, such as type 1a supernovae. And these methods are more direct measurements. And because cosmology loves drama, of course, these two categories don't agree. Indeed, they don't yield the same value. So on the left, in blue, we have the results from the early universe probes. On the right, in red, we have the results for the late universe probes. And there are two possible explanations for this discrepancy. First, there could be unknown systematics for one or both methods. Or second, there could be new physics involved, which would be more exciting. But what we would need is another method whose assumptions and systematics are different from those of the two main categories. Then we would be able to discriminate between these two explanations. And one of the candidate and dependent method is time delay cosmography. So it involves strong gravitational lensing. This phenomenon occurs when the light emitted by a background source is deflected on multiple paths by the gravitation of a foreground mass. Typically, there are 2 or 4 paths. So for a point source, each one of them is detected as an image of the background source. And for an extended source, the observed images will be arcs. So here, the ring is formed by the images of the background galaxy, while the 4 bright spots are the 4 images of its active galactic nucleus. So there is a common analogy to conceive strong gravitational lensing. So consider the background light source as a candle and the foreground mass deflector as the foot of a wine glass. If you look at the candle through the glass, you will see multiple arcs because of the way the light is deflected by the shape of the glass. Similarly, we observe arcs when we look at an extended light source through the gravitational field of a mass deflector, because the light is deflected according to its shape. And this analogy is also perfect to break an awkward silence on a date. You should try that. So all the images take different paths, and these paths have different lengths. So the images don't require the same time to travel from the source to the Earth. We can measure the time delays between the paths by observing a variable source, because then, instead of receiving a continuous signal from all the images, we can distinguish peaks of brightness at different times for different images. And active galactic nuclei are usually used for this purpose. 2 components affect the time delays between the images. The first one comes from the gravitational potential of the mass deflector. The second one comes from the expansion rate of the universe, which we are interested in. So to infer H0 by time delay cosmography, we need to measure the time delays between the images from the light curves and to model the deflector's contribution from the lensing observations. This way, we are able to isolate the H0 contribution to the time delays. But that being said, the analysis presents several challenges. The traditional analysis starts by guessing initial parameters, which includes H0 and a model for the potential. We simulate an observation and time delays from these parameters. After, we compare our simulations to the real data by evaluating a likelihood. Then we update the parameters to maximize this likelihood. And we repeat this process again and again until convergence. It is therefore computationally expensive. Also, because the real likelihood is intractable, this method introduces many approximations. Another issue is that we only have a few lenses to perform time delay cosmography. But the Euclid spacecraft and the Rubin Observatory with the legacy survey of space and time will soon provide thousands of observations. However, the solution brings another problem because analyzing this many lensing systems with the time-consuming traditional method is unfeasible. Fortunately, we already have machine learning tools to accelerate the modeling of the potential. Here are some of them. So conventional neural networks process images, which are the type of data containing information about the lensing potential. Recurrent inference machines are used to solve inverse problem, and reconstructing the potential from lensed images is an inverse problem. Bayesian neural networks can approximate distributions, while other networks provide only point estimates. This is important because we want to assess the uncertainties on the results. So with these neural networks, we could quickly obtain the lensing potentials of a large data set of lenses. But then we still need an efficient way to conduct the inference from the lensing potential and time delays, because the alternative is to run a Markov chain Monte Carlo on every single lens, which is also time-consuming. So to address this issue, we investigate the application of a neural ratio estimator to time delay cosmography. So the main component of a neural ratio estimator is a classifier. To generate the training set, we draw H0 values and lensing configuration from prior distribution. And from them, we simulate lensing potentials and time delays. Then we add noise and feed them to the classifier alongside a value of H0. The classifier is trained with a cross-entropy loss to output the probability that this H0 value is the one that generated these time delays, given these lens potentials. So inputting the lens potentials leaves only the H0 contribution to the time delays to learn. It has been shown that a posterior estimator can be expressed as a function of this classifier. At inference time, we do the same thing, but we extract the inputs from the real data. And we evaluate the probabilities on a grid of H0 values. Then we can plot the output probabilities against H0 values to estimate the posterior distribution. So why is a neural ratio estimator relevant for time delay cosmography? A neural ratio estimator is really fast, as any machine learning framework. Also, a neural ratio estimator is accurate for two reasons. First, it is an unbiased estimator, and second, it is flexible because it doesn't assume any distribution. It is also amortized, which means the same network can be applied simultaneously to all data. We don't have to run an individual procedure for every single lens, as it would be the case with a MCMC. Moreover, a neural ratio estimator can easily be marginalized over a large set of nuisance parameters. So first, we test this idea on a simple analytical problem. So our lenses are singular isothermal ellipsoids. You can see an example of a mass density profile on the left. We add external shear to the deflection angles, and we draw the parameters from wide uniform priors. We add Gaussian noise and only to the time delays because we want to be able to compare the neural ratio estimation with an analytical posterior. So to choose the architecture of our classifier, we look at our data structures. The lens images are a set because their order doesn't matter. Shuffling their input order shouldn't affect the inference. Also, strong gravitational lenses usually produce 2 or 4 images of the background source. So the inputs have a variable length. We implemented a deep set network because it was designed to process sets. It means that it stays invariant under the permutation of its inputs, and it can take a variable number of inputs. To accomplish this, it uses a pooling operation such as a mean, a max, or a sum. Sorry, I'll take a break to drink. Yes, exactly. Okay, so let's see how the neural ratio estimator performs. So these are 3 inference examples. The dashed line represents the true value. The dashed dotted one shows the analytical posterior obtained from our Gaussian noise model. The neural ratio estimator is the full line. We can see that the analytical posterior and the neural ratio estimation agree pretty well on the mean value, but the neural ratio estimator is wider. We think we could improve its precision with further training. But if it stays a bit wider than the analytical one, it wouldn't be the end of the world because the uncertainty on the joint inference of thousands of lenses will be reduced by the size of the dataset. That being said, our uncertainties still need to be accurate, and our neural ratio estimator is not as accurate. Sorry. Sorry about that. So yeah, I'll see I'll be able to finish this. Okay, so our uncertainties are not as accurate as they could be. So here an accurate distribution would fall on the dashed line, but our neural ratio estimator is underconfident, which means it underestimates its own precision or accuracy. Sorry. Okay, so we're still searching why it is underconfident and how to boost its self-esteem. So I will talk about how we can calibrate it in a few moments. Here we have 3 population inferences on data sets of different sizes. So the full line is for a set of 1,000 lenses. The dashed line represents the set with 100 lenses, and the dashed dotted line is for a set of 10 lenses. We can see that the precision improves with the number of lenses, as it should be. The posteriors with 10 and 100 lenses are well aligned with the true value, but the one with 1,000 lenses is a bit off, so we need to investigate this. So on the short term, we will focus on two tasks. Okay, so first the calibration. So we are currently training our neural ratio estimator with a cross entropy loss, which assumes strictly binary classification with one true class. But there is a loss function called Alice, which considers that there is a non-zero probability for each sample to be part of each class. It would be interesting to try it since a neural ratio estimator is not only about classifying accurately, but about classifying with the right probability. Another improvement that we could make is to use a set transformer instead of deep sets. So recall that we needed a neural network architecture that can process inputs of variable length and that ensure the inference. Ensure the invariance of the output under the permutation of its inputs. So deep sets relies on a pooling operation to do this, which discards the information about individual elements. A transformer is a neural network that was developed to process word sequences. So in this example, the transformer evaluates which words in the English sentence are relevant to translate each word in the French one. A set transformer is an adaptation of this to process sets. So it has the same properties as deep sets, but unlike the deep sets pooling operation, it keeps the information about pairwise interactions. So once the neural ratio estimator will be calibrated, we will test its performance, test if its performance holds on realistic uncertainties. To do this, we will simulate lensing observations and realistic time delay measurements. Then we will feed them to a neural network that will model the potentials. The time delays and the potential will be fed to the neural ratio estimator, and we will assess if the accuracy of its estimation is still accurate. So to summarize, there is a tension on the Hubble constant, which is an important cosmological parameter. Time delay cosmography is a method with independent systematics that could help to shed light on this discrepancy. But its traditional analysis is unfeasible with all the upcoming data. So this is why we explore the application of a neural ratio estimator, because it is fast, accurate, and amortized. So for now, we are developing it on a simple analytical problem. Our results indicate that this framework is promising, but it first needs calibration and to pass the test of realistic uncertainties. So thank you very much, and sorry for the coughing.
Thank you very much, Ev, and let's see.
Thank you so much, Eve. Do we have any questions?
Yeah, thanks very much, Eve. This is Simon Beard. Yeah, and congratulations to go for your talk. And I'm also coughing right now. This may be a bit a technical question. How well can the neural network get the astrometry of the point sources in the images? How well can it be reconstructed? Sub-pixel level, or what precision do you expect?
Sorry, I'm not sure I understand. So how the neural ratio estimator can do this? Or?
So does the neural estimator go directly to H0 or to a lens model with predicted image positions first?
Okay, so what we input to the neural ratio estimator is, let's say, 3 time delays with their 3 potentials. So there's a network before that will maybe it will predict the lensing parameters by assuming a model, a macro model. And then from these parameters, we can compute the potential at the position of the images. And with these potentials and the time delays, then our neural ratio estimator can go directly to H0. Is it more clear?
Okay. And the positions of the images come also directly from the neural network, or do you have them pre-measured?
That could be from the network. Yeah, I guess.
Okay, thank you.
Right.
Hi, Eve. This is Anwar Shojib. Thanks a lot for persevering through your talk. So my question is, you mentioned that the likelihood-based inference or the conventional modeling is approximate. I'm wondering how the neural network-based inference is better in that aspect.
Okay, so the approach with the likelihood assumes Gaussian distributions most of the time. A neural ratio estimator does not assume any distribution. It will predict what it was. So this is something we still need to figure out if it. So my neural ratio estimators are trained on data which have a Gaussian noise model, but maybe it could still be accurate on data that don't have a Gaussian noise model. So this is why it is maybe better, is because it doesn't assume any distribution and can adapt to different distributions. Does that answer your question?
Okay, yeah, thank you.
Okay.
So the next thing we have is a short break on 10:40.